Good afternoon. Welcome to week 9 of this NPTEL course on coherence and quantum entanglement. So we will continue looking at two photon interference effects. We looked at some of these effects last time. We saw Hongo-Mandel effect and double pass experiment, and we will look at some other two photon interference effects, and also we will look at the spatial two photon interference effects. So let us begin with the first question. This is the setup for the first question. Let me read out the first question for all of you. It has got three parts. First part: assuming that the coincidence detection system is much faster than the delay time x over c, calculate the coincidence count rate RSI and the one photon count rate RS and RI in terms of x. Describe where do the entangled photons go when minima are observed in the coincidence count rate. Note that this setup is an alternative way of doing quantum lithography. We saw one setup for quantum lithography in the previous week. Design another experimental setup that would keep gamma prime delta L prime equals 1, and that can be used for quantum lithography. So take about a few minutes to read the question again, and then we will start. Okay, so first part, the delay time is x over c. Why? Because this is x by 2 and this over here is also x by 2. And if you look at this straight horizontal path, then in comparison to that, this path travels x by 2, here extra, x by 2, here extra. That makes it a total of x extra. So that's why the delay time is x over c. So part A. First, let us draw the alternatives for coincidence. So these are beam splitters and these are mirrors, and this is the first alternative. The field comes, it gets reflected at the beam splitter and then comes at the second beam splitter, and it can get reflected and transmitted. One photon gets reflected, one photon gets transmitted. And the other alternative, so this is the second alternative. The field gets transmitted at the first beam splitter, and then, oh sorry, I drew the beam splitter wrong orientation. And then upon reaching the second beam splitter, it gets either one photon gets reflected and one photon gets transmitted. Now let us draw the unfolded paths for these alternatives. Now in the first alternative, because of this delay x by 2 here and here, this first alternative, the extra path is x by 2 plus x by 2, that is x. And let us look at the phases. So to go into ds, the signal photon gets reflected at beam splitter, so pi by 2, then mirror, then which is pi, then another mirror which is another pi, and then reflection at the beam splitter, that makes it pi by 2. And for the idler, reflection at the first beam splitter is pi, then mirror, then another mirror, and then transmission, which is no phase change. Now here it gets transmitted all along. Sorry, there is a first beam splitter here also where it's getting transmitted, and transmitted at the second beam splitter, so that makes it 0. And for idler, it is transmitted at the first beam splitter, so 0, and then reflected at the second beam splitter, that makes it pi by 2. So from here we can see that delta L is x, delta L prime is 0, because both these signal idler paths are the same length, and delta phi, so let's do, we will, here there is only pi by 2, so we will subtract 1 pi by 2 over here. So pi by 2 plus pi plus pi plus pi by 2, that makes it what, 2 pi plus pi, 3 pi, 3 pi, and then 4 pi, 5 pi, 5 pi plus pi by 2, and then minus pi by 2, that makes it 5 pi. And 5 pi is equivalent to saying pi, because you will do modulo, you'll take modulus with 2 pi. Now with these alternatives, let us write down the coincidence count. So this is the coincidence count rate. Delta L is x, delta L prime is 0, again we'll take R1 equals R2 equals C by 2, as we have been doing all along. We have been doing this in the previous week as well. R1 equals R2 equals C by 2, and gamma prime of 0 is equal to 1. So this gives me the following. So this is the coincidence count rate. Now let us look at the one photon count rates. So if one photon is at ds, then the other one can be either at ds or di, that is both the photons can go in the same detector or it can go in the other detector. So this means that the one photon count rate Rs will be Rsi plus Rss. That means one going to signal and idler detector, and in this alternative both photons going to the signal detector. And let us draw the alternatives for RSS. So this is one alternative both for RSS, that is reflection at the first beam splitter, and the other alternative is transmission at the first beam splitter. This is the second alternative. And now in the unfolded path representation, this is x because this is x by 2 and this is also x by 2. The phases now. So reflection at a beam splitter is pi by 2, then mirror, then beam splitter again pi by 2. For the other photon also the same, pi by 2 from the beam splitter, pi plus pi from the mirror, and another pi by 2 from the beam splitter. And here it is all transmission, so 0 phase. Now delta L one can see clearly is x. Delta L prime is again 0 because the paths are same for both signal and idler. And delta phi this time is, let's see, 2 pi, 3 pi, 6 pi. 6 pi, which is equivalent to 0 when you take modulus with 2 pi. Thus, in this case, we get RSS is equal to C1 plus gamma x, which is delta L prime 0, so gamma prime 0, which is 1, then cos k naught x, because delta L is x, plus phi, which is 0, so that is this. Let me just write it down as a whole first. So this is the expression when we take R1 equals R2 equals C by 2. So this gives me, when I put in all the values, so therefore RS equals RSI plus RSS, and you can see this gamma x cos k naught x and gamma x cos k naught x, this cancels because here there is plus sign, here there is minus sign. As a result, you get 2C, and this is same for the RI, the other detector single photon count rate, because of from the symmetry of the problem. So this was about coincidence count and one photon count rate. Is there any question? If so, please feel free to put in the chat box or unmute and ask. Okay, someone is asking about these alternatives over here and why I did not draw the other alternatives in which one photon gets reflected and one photon gets transmitted. So let me, is that the question, right? I hope I understood it right. Wait, let me read it once again. Someone is putting in the chat box, can there be other alternatives? Why not consider different alternatives? Is that the question? Okay, just give me a few minutes. Let me just go through the chat box once again. Okay, I think I get the question. Fine. It's the same question that so in the chat box someone clarified what they wanted to ask. So I get the question now. Let me explain. So someone is asking why we did not consider, in this case we considered that both the photons are getting reflected at this beam splitter, and then they split up over here, one reflected, one transmitted. So someone is asking, why not consider that one photon is getting reflected and then goes like this, and sorry, one photon, let's say, goes like this, and the other photon goes like this maybe. So someone is asking, why not split the photons in the very first beam splitter? That's a very valid question, and let me go back to this question and it will make it clear from this statement. The first statement is assuming that the coincidence detection system is much faster than the delay time x over c. So this is the reason why we are not considering. Why? Because in this case, this yellow highlighted path, this yellow path and this green path is there. So yellow path takes an extra time, there's an extra delay x, so extra time x by c will be taken by the yellow path, so they will not arrive at the same time on the detectors, and this will not cause coincidence, not give coincidence, because arrival is at different times. For coincidence, you want arrival at both the detectors simultaneously at the same time. So if one photon is coming after x by c time than the other photon, then that is not detecting a coincidence, because photons are coming at different times. So that's the reason why we have not considered alternatives of this kind. I hope that makes it clear. If yes, please give a thumbs up in the chat box. Okay, so that's clear. Now we can proceed to the next part. Part B says, describe where do the entangled photons go when minima are observed in the coincidence count rate. Note that this setup is an alternative way of doing quantum lithography. So before that, let me show you quantum lithography that we did in the last class, the setup. So in the last week we saw this particular setup. This was the setup for doing quantum lithography. Oh sorry, why did this come up? Yeah, so this was like one particular setup for doing quantum lithography. And if we looked at the alternatives, so these are the alternatives for coincidence in lithography, and one of the alternatives is having a delay, additional delay, as opposed to the other alternative. And here this was the setup for coincidence. We had two beam splitters and a set of an arrangement of mirrors so that the photons reach at the two detectors in coincidence. So this was what we discussed last week. Now let us come back to this setup, and this setup also is can be used for quantum lithography, and we saw what the alternatives for the coincidence are over here. So when a minimum is observed, when a minimum is observed in the coincidence count rate, it means that both the photons go in a single detector. This is what it means when you observe a minimum. I hope it is clear. Next part, design another experimental setup that would keep gamma prime delta L prime equals 1, and that could be used for quantum lithography. So gamma prime delta L prime equals 1. This means that delta L prime is equal to 0. So we have to design a setup in which the paths taken by signal and idler have no path difference, like path length difference. See here, delta L prime is 0 because both the signal idler paths are of the same length. Similarly, here also delta L prime is 0 because signal idler paths are of the exact same length. Oh, sorry. Yeah, so that is how we have to design another setup such that delta L prime is 0. So take about a few minutes to think of a setup. If not, I already have a setup and I will draw it for you. Okay, so let me now show you one particular setup in case you have not thought of something on your own. Sorry. So this is a prism. This is also a prism. And what we have is a pump beam coming from here, gets deflected by the prism, and there's a mirror over here, and then SPDC down conversion can occur, and it will go all the way. It will not get deflected by the prism, it will go straight. And another mirror over here. This will reflect the field to this port. Now what other thing is, it can also go in this direction. I'll explain how. And another mirror. Sorry. So this is the setup. Now this might look confusing to you, so I will draw the alternatives. So the first case is when you have this SPDC, it gets deflected, and now SPDC occurs over here, and if SPDC occurs, then that means it will go over here like this. Okay, so this is one particular case. The other situation can be that the field pump field comes here, then it goes to the crystal, but it does not get down converted, so it goes further, gets deflected by the prism, goes to this mirror, then comes back, traces its path back, deflected by the prism, and now at this point it gets down converted by the crystal, so then it will go over here and then over here. So this is the other possible alternative. Let me draw it for you, that will make things clearer. So one alternative, let me copy paste. One alternative is going to be like this. So the pump field is coming, gets deflected by the prism, gets down converted over here, and then finally gets reflected by the mirror to this port. The other alternative, let me erase out the unnecessary parts. The other alternative, so this is not going to be there. So in this case, what is happening is this pump is going there, it's getting deflected at the prism, it goes there, does not get down converted, so goes there and then deflected by the prism, gets reflected by the mirror back again, then comes back again, and this time it gets down converted. So now this down converted field goes there and then gets reflected by the mirror to this particular port. And as you can see in this setup, so if this is your signal and if this is your idler, and here if this is signal and this is idler, you can clearly see that delta L prime will be 0 because both the signal and idler path lengths are same. So this completes the first question. Again, take about a few minutes to just revise and recapitulate before we move on to the next question. Okay, so now I think we can since there are no more questions, we can move ahead to the next question. Problem 2. What interferes in a two-photon interference? And part B. What is orbital angular momentum described by the state psi given as this? Superposition of CL state. So again, take a few minutes and then we will discuss. This is more like a descriptive question. Okay, so let us now discuss. Part A. In a two-photon interference, the interference is between the different alternatives that lead to a two-photon detection. Part B. In a two-photon, sorry, psi is given as this. Now psi is a superposition state of n OAM modes. Thus, upon OAM measurement, the state will be in OAM mode, on a particular OAM mode L. Which has orbital angular momentum LH cross with probability mod CL squared. So it's a superposition state. When you make a measurement, the state will collapse into one particular OAM state L, and the probability of collapsing into that state is given by mod CL squared. So this completes problem 2, and now we will head into problem 3, the last problem for this week. It is on spatial two-photon wave function. Just take a minute or two to just digest all that we have done before we jump into the spatial domain. Okay, so let me read problem number 3. So this is for spatial two-photon wave function. Let us consider the production of entangled photons using parametric down conversion as described in the figure. So this is the figure. We have a PDC crystal. Down conversion occurs at Z equal to 0, and then we have two detectors at Z. The expression for the two-photon state is given by psi Tp. Psi Tp is given as follows, which is integral over V Qs plus Qi state Qs state Qi. Now the question is, within the assumption of collinear down conversion and paraxial approximation, show that the electric field operators at the two detectors is given by the following. Next part, this is part B. Take Ks equals Ki equals K0 by 2 approximately, where K0 is the central wave vector magnitude of the pump field, and consider the one-dimensional version of this problem so that rho becomes x. Also, take the pump to be a completely spatially coherent Gaussian beam, where omega naught is the pump beam waist. Showed that the two-photon probability amplitude psi Tp is given by this following expression. It's got 3 exponentials, where omega z is the beam waist of the pump at a given z location. and A is a Z dependent constant. Part C finally showed that the two photon coincidence probability to within an overall Z dependent constant is given by this expression for R XSXi. And last part, plot the above two photon coincidence probability and describe it. Okay, so this is going to be a derivation kind of based question. We have to do a lot of derivations to come at these expressions. So take some time to go through it once again, at least the first part, and then we will start. Okay, so let us now start. With part A. So part A is, we are supposed to show the electric field operators at the two detectors. The expression is given as follows. Oh, I need to change the color. So this is the field operator at the detector. We need to evaluate this. Similar expression is for idler as well. So this is KZ. So it is Q is in the XY plane and KS is the total. So that's why KZ, the Z component, is the total minus the XY component. Because if I write KS, This is the expression. So clearly ks squared equals qx squared plus qy squared plus kz squared, which is q squared plus kz squared. Now substituting the expression for kz in the following. Now similarly we will have for the idler also. So this completes part A. Let us now move to part B. Part B is we have to find out the two photon probability amplitude for the 1D version. So just revise this once again, because now it is going to get, we will be making use of these expressions and it will get a little bit involved. So just make sure you understand this expression. We will make use of this expression for the next part. Okay, so let us now proceed. So for 1D version, rho will become x, and we are given this. The pump field profile becomes this. It is given as this. It's a Gaussian. Which is completely spatially coherent. This is psi TP. This is for 1D, where we are replacing rho with x and q with kx. So this we are replacing with ksx and this with kix for 1D. And this was given to us. This is coming from part A. Now psi TP is given by this expression. We know how the annihilation operator acts. So this is the action of the annihilation operator. Thus we have psi TP as the following. So I'm just now doing algebra. So Ks equals Ki equals K naught by 2. So Ks plus Ki is K naught. Now we can write down separate integrals for signal and idler to perform the integral. So now let us look at the first integral. So this is the first integral. Now we will make use of the standard Gaussian integral that we have seen many times now. Now let us make a substitution. And let us open this bracket. Now let us put this in SciTP. So this is psi tp. Now again we will make use of the Gaussian integral. Now I will do some simplification. Opening up the bracket. So 116 alpha in the numerator cancels with the denominator. Now further simplification. Now this 4 alpha in the denominator can also cancel. Now we can combine this A and this term to give another constant. We can call this constant A dash Z, which is Z dependent. Why? Because alpha is omega naught squared over 4 plus I Z over K naught, which is Z dependent. So here alpha squared is there, which is also Z dependent. That's why this amplitude is Z dependent amplitude. Now let us look at the term inside the exponential. So this term we want to look at. Just simplifying it even more. Just this K naught here and here, one of the terms cancels out. That's what I'm doing now. Now opening up the brackets. Now this term cancels out with this in the denominator. Okay, so it's getting a little bit just involved in terms of just simplification and algebra. So if you have any doubt, please feel free to stop me. Let me check if there are some questions in the chat box. Okay, someone is confused in this step. Okay, this step is simple. No, what I just did is I took k naught common over here in the denominator, so that made one k naught come over here, and k naught squared common over here, and one k naught squared comes here, and then this k naught and then this k naught squared. So 1 over k naught divide over 1 over k naught squared, that is k naught squared over k naught, that is k naught. So that's why one additional k naught comes in the numerator. So here it was k naught omega naught squared, additional k naught makes it k naught squared omega naught squared. 4iz, additional k naught makes it 4iz k naught. Here 2 omega naught squared xs xi, k naught was there by taking the LCM, and another k naught, that makes it k naught squared. That was it. That was simple. I think you just missed it. Okay, now taking some terms common. So sorry, now just doing this rationalization by multiplying numerator and denominator by the complex conjugate. So complex conjugate is the following. And this times the complex conjugate, that makes it 4z squared plus k naught squared omega naught 4. Okay. Okay, so this is turning out to be a pretty long derivation, and we are running out of time, and we also have parts B and C to it. Sorry, part B we are doing, part C and part D are there, which are basically dependent on part B. So once we solve part B, only then we can proceed to part C and part D, because they are not independent, they rely on the result from part B. So we cannot just skip part B for now and do part C and part D. And since time is running out, what we can do is we can start from this particular part in the next class, next Saturday at 3 p.m. and we will start from here. We will just revise all these steps that we have done, and then we will take it forward before moving on to the questions from week 10. So right now I think I will stop, because doing any more steps would be futile, as in we will not be able to complete the entire question anyway, since we are short on time. So it's better if you have some questions, you can ask them right now. If not, then let us pause for today, and we will continue from where we left off in the next class. And not just continue, we will actually revise once, so that you're able to recollect what we did, and then we will take it forward. I hope that works. So just a recapitulation, we saw some two photon interference effects, temporal effect, and then we started with the spatial two photon wave function, and then in the next week we will look at spatial two photon interference effects. So this is week 9. We have 3 more weeks, and then most probably we will also have one revision week, an additional problem solving session, wherein we will revise some of the concepts that have been done and also look at some new problems. So that will be all from my side for today. If you have any question, please unmute and ask, or put it up in the chat box. Okay, someone is asking what is the YouTube channel for this course. Okay, I'll put up the link to the YouTube channel for the course in the chat box. This is the channel where I upload all these live problem solving sessions. So if you happen to miss any session, you can go to that YouTube channel and watch it over there. And if you are like somewhat confused, if you did not understand some concept, you can revisit those videos and watch them again at your own convenient time, and you can use them for reference. So that's the channel. I've put it up in the chat box. Okay, so if you don't have any more questions, you may log out from the meeting. We will meet again next week, next Saturday at 3 p.m.